Okay. Now, we can extend this, and coincidentally, I saw this 2 different places yesterday. So, divisibility for polynomials. I saw this in the book you're working in, and then I saw it on Twitter. I think the Theorem of the Day Twitter account shared the divisibility rule for polynomials, or the remainder theorem for polynomials. So I have a polynomial like x cubed plus 3x squared plus 2x plus 1 divided by x minus 1. What's the remainder? Okay, so do you think this looks like a harder problem or the same problem?
I think it's harder.
Think it's harder? Why?
Well, because you don't, well, first of all, can't really say for sure what x is, so this could potentially differ, but the x's could cancel out.
Okay, yeah. What do you think? Do you think this is the same problem as finding the remainders with numbers, or is it a harder problem?
Well, I think a day ago I would have thought this was a harder problem, but now I think it's basically the same problem.
Yeah.
Maybe even a little easier.
So we can think of these as representing the digits, like we had a 10 cubed, 10 squared, and 10.
Yep.
And then we can think of this being sort of the same thing. So this is like the remainder when I have 1,321 divided by 9, or something like
So
that.
you're kind of like in base x here.
Yeah, so you're sort of like in base x. But what we do is we say that our polynomial, so if our polynomial p of x is divisible by x minus 1, we want to write this as another polynomial, h of x times x minus 1, plus the remainder. Now, in polynomials, the remainder always has 1 less power. So with numbers, the remainder is always between 0 and the number.
Yeah.
For polynomials, the remainder has 1 power less. So for when I'm dividing by a linear polynomial, I'm always left with a single number here. Okay.
Alright.
Sorry, I wrote this incorrectly. I want to be able to say my polynomial is another polynomial times x minus 1 plus the remainder. Okay?
Yeah.
Alright. But when I plug in 1 here, the polynomial of 1, evaluated at 1 here, that should equal this, h of 1, times what happens when I plug 1 into x minus 1?
So you
0.
get 0.
It's 0, h of 1. I don't know what this polynomial is, times 0 plus the remainder. And that tells me that the remainder is the polynomial evaluated at
The negative of the constant term of the dividing thing.
Okay. So the remainder here is just whatever I get when I evaluate this polynomial at 1. So I get 1 plus 3 plus 2 plus 1, which is?
Which is 7.
7. So I don't know how this polynomial is, what happens when I divide by x minus 1. But I do know the remainder is 7. And it tells me if I subtract 7 away from here, I'm going to get a polynomial that's divisible by x minus 1. In other words, x cubed plus 3x squared plus 2x minus 6 is divisible by x minus 1. It's pretty amazing. Okay, so how about an absolutely crazy complicated polynomial like x to the 200th plus 3x to the 50th plus x to the 49th minus 200 divided by x minus, how about x plus 1?
So you have to evaluate this.
What's the remainder?
You evaluate this at minus 1. X equals minus 1.
Okay.
So minus 1 to the 200 is 1. And then plus 3 times also 1. So then minus 1.
Minus 1.
Minus 200.
So I get minus 197. Oops.
Pretty neat.
Wow.
Pretty neat. So it's sort of a magic trick. And now we have to, maybe it gets more complicated if I divide by, say, 2x plus 1. What do we do there? And maybe we can figure that out at a later time. But what I wanted to show you was that when you move to polynomials, which are very specific kinds of functions, the rules of arithmetic that we had for figuring out remainders in different mods turn out to be essentially the same thing. So this is one of the very nice properties of polynomials, and in fact it's probably the property that makes polynomial, or at least it's related to the property that makes polynomials very easy to deal with, and kind of why we focus on polynomials rather than just arbitrary functions. Okay, good work this morning, guys.